Hello everyone and welcome to Java tutorial number 16. Today we're going to be talking about multi-threading, and a lot of times people, when they're doing tutorials or books or classes or whatever, love to save multi-threading for later and later and later, and they always put it as an advanced topic. And to be honest, multi-threading in and of itself is not all that difficult. There are a lot of really complicated things you can do with it, certainly, and most of the applications of it are in more complex programs, things like video editing, video rendering, things of that nature. However, there are a lot of use cases where multi-threading can be done very simply, and so today we're going to be talking about simple multi-threading in Java, and then at some later point we might touch up on more complicated, more in-depth Java multi-threading examples, where you're using inter-thread communication techniques, and you're using instances of future, and just having a very confusing program outlook. But for now, we're just looking at the really simple way to do multi-threading, and I guarantee you, if you've watched my other tutorials, this will make sense, assuming you remember the other tutorials. So, the idea of multi-threading came about quite a long time ago, but it's recently, well, not very recently, in the last decade, become a much bigger thing with the release of multi-core processors, because if you ever tried to do some kind of Java program that does some kind of math, say, or whatever, and you have a 4-core processor, even if that program is running at 100%, it's only using 25% of your CPU because it's only using one core. And if you have a single-core system, no big deal. If you have a 4-core system, you can only utilize 25% of your processing power max. And that's kind of a problem, so you want to multi-thread your program. Multi-threading is an idea of setting tasks to be done in parallel. So instead of doing this, then this, then this, do these three things at the same time. So obviously you can't do things that rely on the previous. Like you can't really calculate something like, say, the Fibonacci sequence very well with multi-threading because it depends on recursion. Now you could do it with multi-threading, it just wouldn't have much benefit being multi-threaded because it can't do a bunch of processes simultaneously. Now you could if there was some kind of algorithm for finding the nth term, but as far as doing something recursive, add the last two to get this one, there's not a real good way to do that with multi-threading, especially in a simple way. You could, at the very base layer, multi-thread some of the processes inside of, like, multiplication or something in assembly, possibly, but that's not the point. The point of this is things that can be done in parallel. So, if I have 4 cores, I'm going to probably want 4 threads. I could run 8, I could run 12, I could run 16, but 4 I'm going to be using 100% CPU, 8 I'm going to be still using 100%, it doesn't go over that, or 400% CPU as you'll sometimes see it described. And so I have an instance running here in a VPS, and this is generating a bunch of prime numbers, and that's what we're going to be doing today. We're going to be making a program that generates a bunch of primes. This is actually generating Sophie's Germanic primes, but that's primes. And as you can see here, this is the current progress of it, and this is the same server. This is on this is a window of HTOP running on the same VPS. So as you can see here, Sophie's prime threaded final is running. Each one's running at almost 100% CPU. A little bit of CPU is also being used by a version of Minecraft CraftBucket I have running right now, but most of it's being used by the Java jar file. So we're going to be showing how to do that today. And multi-threading in and of itself, like I said, is not hard. It's when you start adding more onto it. So this will be extremely simple. We already have a basic skeleton here of these two classes. Main class is going to be where pretty much it's kind of the manager, it's the boss that goes around and tells people what to do. The prime threads are like the workers. They are told what to do and then they do it, and then they put it on the assembly line, and then the assembly line rolls by. And so in here we have already a nice, perfect, beautiful written method that's called isPrime. And isPrime is basically just a method that returns whether a number is prime. No big deal. Interestingly enough here, we do have to do a special case for 2, but I'm not really going to explain how this works. It's pretty straightforward, but that's not the point of this tutorial. So just imagine this as a black box. IsPrime is a black box, you just call it and it tells you whether it's prime or not. Alright, cool, because that's not what we're multi-threading. We're multi-threading the entire process, and isPrime is just a sub-part of that. So, isPrime, pretend it's a little black box, and you put something in, and you get either true or false out, and then you use that true or false to do something else. So isPrime is a black box. We're implementing Runnable, and I'm not going to go way into Runnable. Let's see how Eclipse likes to explain it. Interface is designed to provide a common protocol for objects at which to execute code at which they are active. Basically, it enables things to be multi-threaded. It has more uses than that, but it basically allows these different classes to be multi-threaded. There's multiple ways to do multi-threading. This is the one I like to do. I find this to be the easiest one, the most logical, straightforward, but there's other ways too. You can extend thread instead and go from there. But implements runnable is a quick way to make it so that it can be multi-threaded. And there's a couple things you want to make sure of. So you'll see we have class variables here, but you'll see that we don't have public static before them, or private static, or whatever. We don't have some kind of modifier like that. With multi-threading, if you do that, the threads will especially the way we're managing threads, the threads will all look the same, and so they're all going to be doing the same math because they're sharing some kind of memory pool. We want them each to have their own separate one, so these are all going to be separate. They're not going to be defined as public static or whatever, private static or whatever. They're just going to be defined like they would in a normal class, and this works perfectly fine for threads. It's something to keep in mind. And keep in mind that this is not the most efficient way to do this program. It is simply one way to do it, and a more efficient way would be to have one a better is-prime algorithm, and another way to make it more efficient would be to have inter-thread communications, and at the end, when we combine all the information together, combine the little packages of primes, to have that done sequentially as threads run, where they're offloading things onto into a RAM pile instead of onto the disk. So that would be the more efficient, but way more complicated way. So this program isn't extremely efficient. It's just, it works. And it's simple to understand, and it's simple to learn as a intro to multi-threading. So that's why this isn't the most efficient it could be. Run is where a thread starts. It's kind of like public static void main string args, kind of like that. But you can't give it variables and stuff. Here we have our object instantiation, and so we can instantiate objects before we put them into a thread container, and we'll explain all that in just a second. You shouldn't have to understand that right now. We'll get into that. But basically, you can instantiate the object and then start it. So that's what we're doing. We're going to instantiate the object, and the basic layout of this program is, and let's think of the logic. This is always good with any kind of even small-scale project like this, to think of the general logic you're going to want so you can implement it as you go instead of having to go back and back and back and forth and back and forth, which we're still going to do a bit. But the general idea is that we want to, in the main class, have some kind of number that we know we want to generate all the primes from 1 up to that number. Okay? Seems simple enough, right? Now, we don't want to worry about special cases like 1 is technically not a prime because primes have 2 factors and 1 only has 1 factor, which is 1 in itself, but 1 and itself are the same, so it's technically not prime. We're not going to try to worry about all those different things or a more efficient prime algorithm. We're simply going to pretend the is prime is a black box, and that each worker, each thread, has the ability to put something into that box and get something out, and as a result, it's able to work. It's able to test whether numbers are prime and somehow record them. Now, instead of having hash tables and future and everything here for Java to be able to communicate between threads and threads communicate back to the main class, we're just going to write the information to a file, and the main class is going to pull it out of the file and recombine it. So basically, it's like having each worker make a certain part of a toy, and then the boss comes by and does the special step of just putting all the pieces together and sends it on its way. And that part's pretty easy, so the boss can do that. The workers, however, are doing the hard labor of finding whether things are prime, and if they are prime, putting them in a pile. And that pile is going to be a flat file format, and each one's going to make a different file that's sequentially named so our main class can find them. And we want our program to be extendable so that if we have an 8-core processor, instead of having to redo the program logic, we can just put 8 instead of 4 for a variable. And it'll automatically scale to that many processors. And that's where it gets a little bit tricky with the logic, but it still makes sense. You just have to kind of think about it a bit. So, let's define a class variable called, well, we already have stop, and let's set stop to, let's do 800,000. Okay, so we're generating all primes between 1 and 800,000 inclusive, but 800,000 wouldn't get hit because it's even. Thread count, I have a 4-core processor, so I want to set, I have a Core i5 2500K, so I'm going to set that to 4. And I'll show you in a minute. Actually, let's set that to 3. Yeah, let's leave it at 4. And we'll change that in the future, and you'll see how it affects the program. So, our main method is where it starts, so let's do a system.out.println statement spawning threads, and then it'll spawn threads. So we have this thread object here, and let's worry about the thread object logic real quick. Let's talk about how that works and what that accomplishes. So the thread object itself, the prime thread we call it, we want to have a constructor first of all to be able to set these variables. So int start value, int stop value, string file name, and a boolean is lead. And it's going to yell at us, and it's going to give us this funny line, and it's mainly because I put a semicolon here, which is completely ridiculous. And so now we have our constructor. So we tell the object, hey, and if any of this doesn't sound familiar, please go back to previous tutorials and watch them, and then it'll make sense and come back, because that way everything will make sense for you. So prime thread, we want this constructor to be able to take a start value and a stop value from main class, as well as the file name it's going to write to, which we'll sequentially name, and whether it's the lead or not. Now, by lead, this is not a big multi-threading related thing. Lead is just simply saying, do I want this one to be the one that shows progress or not? Due to the nature of primes, I want the one that shows progress to be the prime, I want the thread that shows progress to be the thread that's processing the biggest number of primes. So like, I'll have 1 to 100,000 and 100,001 to 200,000. They're both the same amount of primes that they're calculating. However, the 100,001 to 200,000 is going to have bigger numbers, so I want that one to display progress because that one is going to finish last. This is just a math concept, not even programming. Just because for each number, a number in the 100 to 200,000 range has more factors, so the program is going to be like, okay, we're going good, and instead of finding whether it's prime or not really quickly, it's going to take a little bit longer for those bigger numbers to find out whether they're prime. Naturally, if I gave you 118 or 119 and I asked you is it prime, you could figure that out on paper. If I gave you 400 million and 417,892,417, could you tell me whether that was prime on paper? Yes, but it would take you forever because you have to do more calculations to find out. So that's why the thread that's doing the biggest numbers is going to be the one that shows progress, because I want the one that shows progress to finish last, so that it shows progress for the entire thing running. That way we don't have progress like, okay, thread's done, and then another thread's still running for another 10 hours, that kind of thing. So we want our last thread to be isLead, so we'll take care of that in main class, but that's basically what isLead does. And we'll do start equals start value. And now I could call this int start, int stop, and then I do just this dot start equals start, as I've probably mentioned earlier, and the this keyword specifies that it's one of the class variables. And as you can see, it highlights that one instead of that. So this dot start, and it highlights those two, not that, so you can see where it refers to. However, I'm doing this just so the logic is a little bit easier to follow, so it makes sense. So start equals start value, stop equals stop value, file equals file name, file's name, and lead equals isLead. Now, for some reason it's yelling at us, start value capital V. Okay, we're good. So we have our constructor made, and constructor, again, remember, is when you instantiate an object, it's the parameters that you pass to it. So now this object knows what it's starting at and what it's ending at, the name of the file that it's saving to, and whether it's showing progress or not, which is all we need here. Now we need to actually do the logic of finding if it's prime or not, and if it is, recording it somehow. So I've talked about array lists before. I don't know what tutorial, like around the 8 range or so, I think. So if you don't remember what they are, they're basically arrays that don't have a fixed size. They're more advanced than that, but that's what they function as. They're arrays that you could just keep adding to. It's just like if you have a regular array, an int array or whatever, and you set it to X, then you only have a sheet of paper with X lines on it. If you make an array list, you can add another piece of paper whenever you want. And you don't even have to add the paper, it does it for you. So array lists are very easy to work with. So we're going to create an array list of type integer, and we're going to call it primes equals new array list integer. So we've created our array list and we call it primes. So now we're going to want to do a for loop. So we're going to want to start at start. It's nicely named like that. And we want to end at stop. and we want to increment. We could do I is less than or equal to if we wanted to, whatever. And essentially at this point we really don't have that much going for us per se. We have just this for loop that's going to start at start and stop at stop, and it doesn't seem like it's that great. Now, inside we have to actually do the prime logic and add to the array list. So if is prime I, and actually let's do I plus equals 2. And we'll assume I is starting on an odd number. And that way, odd, 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 we never hit an even. Evens are never prime unless you're 2. And so it'll skip all the evens. So let's do plus equals 2. And if I is prime, then we want to do primes.add I. This part of the program is really simple. If I is prime, add I to primes, because it's prime. So, then we want to say if it's lead, so if it's displaying progress, then if, or actually let's do a compound if statement. So 2 ampersands is and, or ampersands, the and symbol, whatever they're called. Lead, if lead is true, and if I plus 1 mod 10,000 is equal to 0. Let me explain this. So the mod operator, first of all, takes a number, divides it by the first number, divides it by the second number, and returns the remainder. So 19 mod 10 is 9, 9 mod 10 is 9, 10 mod 10 is 0, 17 mod 10 is 7, 482 mod 10 is 2. So it's the remainder when you divide. I plus 1 makes it even, because I is always going to be odd if we do this right, because we're plus equaling 2. So 1, 3, 5, 7, we're going to get to 99,999, 10,001. So we want to add 1 to it to make it so that it will always be even when we're doing this comparison. And in here we just want to do system.out.oop, system.out.println, and we want to say lead plus, or we want to say I, sorry, plus, and whoop, I didn't want to enter there, out of, plus, and then stop. One problem with this is when it's showing progress, it'll show like, it'll start at 500,000 out of 600,000 if you have like 6 threads and each one is 100,000 or something. So it won't be like, it won't start at 0 out of blank, it'll start at the starting value. However, for the simple program, it's not a big deal. If this was some kind of commercial application or something, we'd just do a little bit of math to make it into a percent. So, big deal. But we're just going to go with this because it's simple and easy to understand and quick and fast. So, it's going to print progress if it is a lead. So we're basically done with this class. We might be coming back to it a little bit later, but we need to add one more thing, which is how the worker outputs its work. Normally, if this was just a method, we'd return it. We'd say return primes. You can't do that with a thread. There are ways for threads to communicate with their parent class. It's a little bit more confusing. You can do it through like a hash table. You could do it through using future. However, we're just going to write it to a file. So we're going to do a try catch block. Because print writers like try catch blocks. And we're going to make a print writer. And we're just going to call it print equals new print writer new file. So if you'll remember, file is the name of the file we're writing to. We create a file object with that name, and then we create a print writer object of that file with that name. So basically this lets us print out to a file called whatever the file name is, so like 1.txt, 2.txt. Makes it simple. Then we'll do for int I equals 0, I is smaller than primes.size, I plus plus. Now explaining this, primes.size is how many primes there are. We want to go less than because we're starting at 0. So if you had 4 primes, you'd want, and you start at 0, you'd want primes in slot 0, 1, 2, and 3. You'd never want to touch 4 because there isn't a prime in slot 4 because you start counting at 0. So that's why you do less than, not less than or equal to. And then you do print.println, and you just put, primes.get I. So it'll first do the prime at position 0 in the array list, then 1, then 2, then 3, then 4, all the way up to the size of the primes minus 1. So if you had 1,000,000 primes, they'd be occupying slots 0 through 999,999. Or if you had an array list that had 1,000,001, it'd be 0 to 1,000,000 for the slots. So we want to get each one of those primes and just print it out, and then at the end we want to do print.close. This kind of flushes the file out of memory onto the hard disk and tells it, okay, we're done writing the file. And after that, we're pretty much done with this thread. We might be coming back to it to change a little bit of logic, but that's the basic idea of it. So after we say spawning threads, we actually want to spawn threads. So the best way to do that is probably to put those into an array list as well. You could put them into an int array, but then you'd have more things to change and it gets a little bit more confusing. So I'm just going to use an array list here again. And the basic logic of this is that you want to iterate through all the up from 0 to thread count -1, and you want to make a thread for each time you do that. So let's do a for loop. For int I equals 0, I is smaller than thread count. Remember, if we have 4 threads, we want threads 0, 1, 2, and 3. And I plus plus. We'll create an array list out here. Array list thread equals threads equals new array list thread. Thread is basically, well, it's a thread. You put an object inside of thread, and that object implements runnable, and then you can start it like as if it's a thread, because it is a thread. And then so you iterate through it, and every time you run this, you want to create a thread. So threads.add new thread, new prime thread, then you pass it the values. So let's talk about the values. Well, let's talk about this real quick, and then we'll talk about the values. So you're adding a new thread object, and to make that new thread object, you're making a prime thread object. So you're making a prime thread, you're putting that inside of a thread, and then you're adding that thread, kind of a sphere with a layer inside of it, you're adding that thread into your array list threads, so like a table of all the threads you have running, basically. So, table is a loose term, not actually technically the table that you think of in computer science, but just kind of a general knowledge table. Table of general knowledge. So, we want to calculate what our parameters are going to be. So, let's first make an integer, increment amount, and set that equal to stop divided by thread count. The logic here is that if stop's 800,000 and you have 4 threads, you want to divide this equally. So you divide thread count into stop. So stop is 800,000, you have 4 threads. Each thread wants to do, or you want each thread to do 200,000 numbers. Now, being that the threads are going to finish, the earlier numbered threads are going to finish before the later numbered threads just because they have less work to do, even though they're finding in the same range, they're like looking at the same number of numbers to tell whether they're prime or not. You got to remember that those numbers are smaller, so they're easier to tell. So if you were really trying to make this optimal, you would do a couple tests or something, and you would find about the distribution at which they all finish around the same time, and then set them to that. Now, in the program I'm running here, I have something going along the lines of I do 35% of them for the first, 30% for the second one, and then I split the remainder almost equally between the last ones, but with a little bit skew. So I have 35 and 30, so that's already 65, and then I think I do 22, or actually this one does 64 for the first 2, but anyway, it has uneven distribution where it gives a larger range to the first ones because each one in that range is easier to do. And I found that to be kind of, not the sweet spot, but as close as I was willing to spend time getting. Again, this is just a program for fun, just for the heck of it, so not a big deal. But doing some tests and finding out, how you distribute them. Here we're just going to pretend that distributing them even's fine. So increment amount is that. And for scaling now, we want to start at 1, so int starting equals 1. And every time we run through it, we want to add increment amount to starting. So if we start at 1, then our increment amount is 200,001, or 200,000. Then the next one we're going to want to start with 200,000 and 200,001. So we're going to do starting plus increment amount, and then we're going to put after this the name, so I plus .txt. So, 0.text, 1.text, 2.text, 3.text, all the way down the row to 548 billion.text, and that's when it runs out of memory and nothing works. and then we want to send it false. And we'll want to do that for every thread but the final one. So if I plus 1 is equal to thread count, is not equal to, so if it's not the final thread, we want to do this. So we want to do this kind of a thing here. We want to run this thread, we want to add this thread with false if it's not the last one, else if it is the last one, we want it to be true. So because that's our final thread, that's the one we want to print information, so true. Indent, haha. So now we've accumulated all the threads we want. Now we got to go through and start them. So we'll do another for loop for int I equals 0, I smaller than threads dot size, and I plus plus threads dot get I dot start. And it's might yell at us, and it doesn't. All right, cool. Sometimes for some of this stuff, you never know whether it's going to ask for a try catch because it's been a while. But anyway, so now we start all of our threads, and once we're done starting them, we have to join them. Joining tells this program to basically wait until all the threads are done. It's the simplest way to do that, I find. So then for int I equals 0, I is smaller than threads dot size, I plus plus threads dot get I dot join. This one is the one that wants a try catch. So try catch exception E, or whatever you want to call it, and we don't even do anything with the exception, nobody cares. So, and if you do care, you can add it yourself. So, because the source code will be in a download in the description. So, we join all our threads, and then after we're done joining threads, we want to go through and pull out all the information from the files and add them all, not add, but concatenate them all together into a new file. So before we get all into that, let's check to see if this works. So this folder, I'm going to delete these. It's from a previous thing. So if I run this, it should generate 4 files, 0, 1, 2, and 3.txt. Let's try it. Run. There's our progress. Looking good, and we have 0, 1, 2, and 3 here. Let me run that again and show you the CPU usage. As you'll see, it put 1 here. Alright, big deal. If that really is an issue, you can start it counting at 3. Whatever. But anyhow, I'm just going to delete these, and I'm going to show you it running again. And I'm actually going to increase this to 8 million so that we get the feel. So while this is running, since I have 4 cores, I should see, and I have 4 threads, I should see 100% CPU usage. The reason Java isn't using 100% is because some other Windows processes are using CPU time as well. So we're having to wait on letting Desktop Windows Manager and Steam and everything else, we're giving them CPU time. So Java's using whatever's left, which right now is hovering around 84 to 87%. And Desktop Window Manager is eating up almost 10% of our CPU, which is kind of a waste. But if we go to this VPS here, which is running, you'll see this one's at 100%, and it has other processes eating up. I have CraftBucket in this instance running basically a Minecraft server. That's a spare Minecraft server, not my main one. That one's just one I do with friends. But there's not really much reason to let this run. That was just to illustrate the CPU usage, and my desktop's lagging from it, which it should be. That's a good sign. It means it's working. So I'm just going to kill it here. And we're going to reduce this back to 800,000 so it actually goes fast. You'll see there's no files here because none of the threads finished. So in prime thread, we wrote our files. So in main class, we got to bring those files back together. So once we've joined them all, once they're all done, we want to do some kind of going through and grabbing the files and putting them all together into one. So that's the easy part of this tutorial probably. So for int, let's create first an array list primes equals new array list integer, and we'll have to put integer here. Integer. Okay, so we have an array list, and we're just going to add all the primes sequentially to it. So for int I equals 0, I is smaller than threads dot get. or threads dot size I plus plus. We're going to, for each file, each thread represents one file because each thread made a file, and we're going to use the same numbering system we used here, I plus text, so 0, 1, 2, and 3 in this instance, 0, 1, 2, and 3 dot text if they were here. Let's run this actually so we get those files there so we can look at them. And there they are. And if we look in 0, those are all primes. If we look in 3, those are all primes. Now you'll notice a problem with these, in that each one of these all have the same primes in them. So that's a quick fix. What we did is here we forgot to increment starting. So starting plus equals increment amount. And that works just to, the next time around it starts at where this ended essentially. So let's run this again real quick and we'll get our new files. And it'll lag us out like crap. And that's why it ran so fast earlier, because all the threads are doing smaller numbers. This one's doing larger numbers, so this one we actually see quite a bit of CPU usage. It's getting eaten up. However, one of the threads, it looks like 2 of the threads are already finished, and this thread's almost done. Now this thread's the only one remaining, and as you can see, since that's the last thread, that's the last one to finish. So then we go over here, and 3 actually does have the primes you'd expect. So we're good. We fixed that issue, and it wasn't any screaming or crying or pain involved. Interesting that that's a prime. I didn't know that. Okay, but anyhow, so now we got to rejoin those files together. So for each thread, we want to pull all the data out of the file. So scanner scan equals new scanner new file I plus .txt. So that creates a scanner object, and the scanner is yelling at us because it wants to try. Whoa, we don't want to throw anything. Throwing is bad, it's dangerous. Throwing things across the room is unsafe. Unchecked, unsafe behaviors. Ha ha ha, Java humor. So we'll do our try-catch block here. And then we'll take it from there. But basically we create a scanner, and it's kind of funny how starting doesn't need a try-catch, but ending, joining does. The reason is because joining can throw exceptions a lot, and start doesn't really have exceptions that it's going to be throwing usually, so don't have to worry about that. But anyway, just got to keep all that straight. It's good to have an IDE to remind you. It's really nice. I recommend Eclipse BlueJ. Eclipse and BlueJ. I think I just got a text. But anyhow, so we create our scanner, and we do while scan.hasNextInt primes.addNext scan.next int. If this doesn't look familiar, go back to some of the previous tutorials where we talked about the scanner object and how it worked in detail. But basically we're saying while the scanner still has another integer available, we're going to pull that integer out and put it in primes. And remember, this is scanning from the file that's already made of primes, so we don't have to do any prime checking here. And so we're going to do that for each one. And then at the end, we should have a array list integer primes that just contains all the primes. So then we'll do another for loop for int I equals 0. Oh, and then once we're done with this, we'll do scan.close, and then we'll do file f equals new file I plus .txt, and it'll do f.delete. Delete that file, don't want it here. In fact, we could make this a little bit more efficient. X loop and F. There we go. So that's a little bit more clean and logical. And then we'll do this for loop here. I is smaller than primes.size, I plus plus, and then we'll just do a try catch block. And what do we want to catch? Exception E. Let's do Q. Q is a cool letter. I was about to say number. Q is a cool number. In algebra, maybe. So anyway, we're going to want to create a print writer. Oh, we'll want to do this actually outside. We want to do the try catch with the for loop inside of it. That way we can we don't create a new print writer object every time. That would not work well. So we want to, inside our try catch, do print writer. Let's just call it print equals new print writer, and we'll create a new file, and we'll just call it primes.txt or whatever. No one really cares. So Then we iterate through this for loop, and for every prime we have, we just want to print it out. Print.println primes, or what am I doing? What is it with me and double quotes today? Primes.get I. And then once we're all done with that for loop, we want to do print.close. Again, print.close kind of flushes out that file from the memory onto the hard disk. And at some point, if you're adding so much stuff to a file that it gets beyond what your memory wants to hold, it'll flush it manually to a file. So even if you don't have print.close, if you're adding enough stuff, eventually most of that file will be intact. But print.close, you still want it there for obvious reasons, because then the remaining portion that's in memory that hasn't gotten too big to be flushed yet would all be lost. So print.close, just do it. Buckle up, it's safe. And so if we run this, spawning threads, it does its progress, we cross our fingers and we hope it works. We look here and we watch patiently, we're like, okay, you can do it, I know you can do it. And it's getting almost halfway done, but even when it's halfway done, it's not truly halfway done. And in a second I'll do a proof of concept for why we want the last thread to do the progress, but that'll be in a second. Longer than a second. Okay, so that finished, and we have this one file called primes. Let's open it up. And yes, it starts with 1, and it goes through 799,999. So we have one file called primes that, using multi-threading, we effectively calculated using all of our CPU. So if I run this again, just to show you, it is using 100% CPU here. Or at least as much CPU as is left for it to use. Because, again, Desktop Window Manager is using a ton. Now let's do the proof of concept that I was talking about real quick for why you want the last thread to show the progress. So just to show it, I'm going to do thread plus I plus finished. And that way you'll see in what speed the threads finish. So thread 0 will finish first, 1 will finish second, 2 will finish third, and 3 will finish last. So let's just delete this, we don't need that. And if we run this, spawning threads, here we go. And you'll see as this thread 0 already finished. And then thread 1's going to finish in 3, 2, there we go. And then thread 2 will finish in probably around the 7,600 mark, or 750,000 mark, okay? And then thread 3 finishes. So if we had the progress at thread 1, or thread 0, it would have printed progress all the way up to here when it finished, and then all this we wouldn't have gotten any feedback for because thread 0 was already finished. Thread 3, however, was the last to finish, so that one displaying progress is optimal because it shows progress the entire time. So, thank you for joining me. All this source code will be in a download in the description below. As well in there is a jar file that is built for up to 8 processors. Oh, let me change one thing real quick. Let me change thread count to 2 and show you what happens. 2 will still work, it'll just take twice as long. If we look here, you'll see Java only hits around 50% usage. The reason is because each thread is using one core on the processor, so each thread only accomplishes one thing. Now you'll see once this finishes, we'll look and we'll still have the prime file and it'll be finished and done and working and everything will be nice. It just takes twice as long to run, approximately. So, as you can see here by the around 25%, thread 0 already finished, now we're just waiting for this thread to finish here. And if we put thread count to 8, it'd still work perfectly fine, and I'll show you that in just a second too. And that would mean that then on like the AMD bulldozers, it'd work amazing, you know, just destroy all the prime numbers in the world. So if we go over here and we look in primes, and it's still all perfect. Oop, all perfect. So we're good. Let's change this to 8 and see what happens for a bulldozer architecture. And you'll see which ones finish first. This one's kind of interesting, actually. Thread 0 finishes like way quick, then thread 1, then thread 2, and it just kind of goes in that pattern. Those finish at the same time because those are running concurrently. And the way Java handles multi-threading is basically well, the way a system handles multi-threading is if you have like 8 threads, it'll just give each one half of one core kind of time. It'll just kind of switch them off, on and off. And if you have hyper-threading, then it can take advantage of better time management and switching. But so anyway, there's an example in the description below. There's a zip folder, and in that zip folder, you'll find all the source code for this. These 2 files, the source code. You will find a jar file that when you open it up, it'll ask you how many primes you want to generate. and then it'll ask you how many threads you want, and then it'll generate all the primes from 1 to 1,000,000. And you'll also find the list of primes in that zip folder. So thank you for joining me, and we will see you next time. If you have any questions, feel free to leave them in the comments.